think this is like Fireside Chat 40 or 41. So we've
done quite a few of these. For those of you that are new to either the Design of Experiments course or the Fireside Chats, this is something that I run every month with a guest speaker, and we talk about specific topics or applications of experimental design. We also have some time at the end of the guest presentation for Q&A. And this is a really good time for you to ask questions, and they could either be about something that our guest has talked about, or it could be something that has interested you, or if you have some curiosity about that we've covered in one of the Coursera courses, or if you have a question that is specific to a particular problem that you're encountering. We'll provide help for that if we can. If you are on Coursera, we record these fireside chats and we post the recordings in the courses, and they're in the resources tab of your course. And I would encourage you to look back over the list of these many fireside chats that we've recorded. There are some really wonderful topics there and things that you would maybe many of you would find extremely interesting. Quick reminder, please keep your microphones muted and your cameras off so that we don't have any extraneous noise or other disturbances. When I'm on Zoom at home, my dog likes to bark, and I know people find it distracting. If you want to send in a question, the best way to do that is using the chat function on the Zoom menu bar. And you can start typing in that question anytime. You don't have to wait until we get to the Q&A session. If your question doesn't get answered during this time period, we'll respond to it in Coursera for those of you that are enrolled in the course. So that's a little bit of information about how we're going to run things. And with that, we're ready to introduce our guest. And our guest today is Dr. Ryan Lekivetz, who is a senior manager of advanced analytics R&D at JUMP, and he leads the R&D development effort for the Design of Experiments and Reliability team. Ryan has a doctorate in statistics from Simon Fraser University. He's published a lot on experimental design in different peer-reviewed journals. He holds patents that he shares with his team members. His research interests really include most of the experimental design field, combinatorial testing, and the intersection of the two. So with that, I'd like to have Ryan take over the floor, and you can start your presentation anytime you'd like.
All right. Well, thank you so much for having me. And so really, it's my pleasure to talk today about the testing of statistical software, right? And I'll say this is something that when I started at JUMP, it wasn't obvious to me just how connected testing software is to design of experiments. So here's kind of an outline of what I'm going to talk about today. So really, just what is software testing? The testing challenge. We get a new student that comes to JUMP, and they're tasked with testing JUMP. What does that actually mean? Then test selection as a designed experiment. And as time allows, so I'm going to introduce this idea of covering arrays, and then a couple of examples that come right from JUMP. So one using XGBoost, and another with the JUMP profiler, the prediction profiler. So what is software testing? Right? You can go to your favorite internet browser and plug in, well, what is software testing? And here are some pretty typical definitions that you're going to find. To show the software works as intended, to ensure there are no bugs in the software, assures us the software does what it's supposed to do. So these all seem like pretty reasonable definitions of what is software testing. Now, for the purposes of this talk, I'm going to say no. These are not the definitions that we're going to use. And so why is that? Well, if you look at the wording here, So these are going to approach the problem as showing that the software works, right? Which isn't a bad thing. But let's just say if you ask a colleague, right, maybe you've developed your own software, or even if it's something as simple as just reading over an email, right? So saying, can you check that this works versus try and break it, right? And so it's the same thing. If I want to ask a colleague, does this document look okay versus bring out your red pen and mark it up as much as you want, right? And so for our purpose here, the definition I'm going to be using in this talk for what is software testing. So testing is the process of executing a program with the intent of finding errors. So emphasis on that finding errors. So what this is going to tell us, if I'm a tester, my purpose is to try to break the software. Now you can imagine what's the nice thing about that? Well, if the tester or the test engineer can break the software, well, then we can go about and fix those bugs, right? And by fixing those bugs, then we can go back to that definition, right? So if we've tried our best to break the software, found the bugs and can fix them, then we can actually go back to those definitions, right? And so again, that's throughout this talk, just keep that in mind, that our purpose here is to try to break the software. Well, so a natural question is, okay, that's great. Maybe I want to try to find problems in the software, but where are the bugs? Right? And so there's a famous quote from the software engineering community from Boris Beiser that says, bugs lurk in corners and congregate at boundaries. And so what does that mean? Well, just like the insects that we think of for bugs, it turns out to be the same way when we're testing any kind of complex system. So those boundaries are what you might think of as extreme values, right? Maybe I plug in an input that doesn't work when I put in something like a 0. Or if I put in an input that's way too large, something's going to have a problem. Now, the corners that Beiser is talking about are actually the same way that we think about interactions in design of experiments. It says there's these two inputs that are working together that on their own may not cause a problem, but when I'm using them in conjunction, so when I look at those corners, that's when I'm going to find a problem. And so if you think about what does that mean from a coding standpoint, well, it might be in somewhere like an if statement, right? That I haven't thought about one of those different paths that can occur when I'm going through that. So now what is the testing challenge for, right? So if I'm a new tester, what's my testing challenge going to be? Well, so I'd break this down into really 3 key components here, right? So there's a selection problem, right? So how do you select the test cases from the input space? And so in particular, that you want to maximize your chance of finding faults or finding those bugs. There's a quality problem, right? If I'm going to go to my manager as a tester and I'm going to say, well, I did 100 tests. Is that enough? Can I make an informed assertion about the fitness for use, right? So if I want to be able to release JMP to the public, what does that mean if I've done 100 tests? If I say that I've done 1,000, right? So it's that idea of fitness for use. Now I'll say a particularly difficult problem for statistical software is the so-called Oracle problem. And that's, so how do you actually determine expected behavior for each test case? Right? And so I'll just take a little bit of an aside here. I would say the Oracle problem is one of the most fascinating things about the testing problem. And so the Oracle problem, when we're talking about testing, it really just says, well, how do I determine if a test outcome is what was expected? Right? So I have my set of inputs that I'm going to give to the software, and then I get something back from it. Now, usually if you look at statistical software, there's a lot of focus on numerical accuracy. So it'll say down to the 13th decimal point, did things match up? But if you think about something like JMP, we often have a lot more to do. And so really our test engineers are often faced with, well, how are they going to go about determining that expected outcome? And what does it mean if the results change from day to day? Right? Sometimes an algorithm may have improved, so the new results perhaps are better, right? But perhaps something else is broken. And so how do you know as a tester that something's gone wrong? And I'll also say, unfortunately, for a lot of what we're dealing with with statistical software, especially as people have gotten more used to using things like machine learning algorithms, it falls under this class of what we would call non-testable software. So in that, there's really no oracle. I don't know what the correct answer is, or maybe it's theoretically possible, but practically too difficult to determine the correct output. Right? And so often what we have to rely on is something called a partial oracle, which is, so if something like jump crashes, if I do something to the system and jump crashes, well, I know that that's already a failure without knowing the correct answer. But the other thing we'll often rely on is what you would call a pseudo-oracle, right? And so that's going to be an independently written oracle. And so by that, our test engineers are often tasked with effectively trying to recreate the algorithm all on their own and check that those results match, right? And so to put this a little bit more generally, so this oracle problem, again, something like a software crash, that can be a pretty obvious mistake, but something it's like timing, right? If I expect the results within seconds, I'm not willing to wait 10 minutes for something that I was hoping was only going to take 2 or 3 seconds. How do we handle things like visualization? Right, so there are a lot of graphs that we present in JUMP, a lot of interactivity. How do we test things like that? Sets of statistics, the numerics, again, how close is going to be good enough? The other challenging part is that there may not be existing packages that a test engineer can use. Right, so it's not uncommon that we'll have developers at JUMP who are working on, publishing a paper or some of the recent literature that they're trying to implement. Well, there may not be the existing packages for that. So in some sense, a test engineer has to go about figuring out how can they implement that in their own way to check that these results are correct. So again, that oracle problem really is a very difficult part that we have to deal with. But for our purposes here, if we think about this, taking a step back and thinking of this from a design of experiments problem, so let's revisit that selection problem and the quality problem. So in particular, if you think of that selection problem, how do you select test cases from the input space of a system? That sounds a lot like design of experiments, right? And we have a set of inputs. How are we going to go about setting the values for those inputs? And in particular here, we have a goal of maximizing that chance of finding faults. Now, at the same time, that quality problem, that's kind of saying, well, how good is our design, right? So if I can create this design of experiments or this test suite, can it tell me anything about the fitness of use for the software when it goes out? Right. Now, if you have some familiarity with testing software, this is a common thing that you hear about. So this idea of unit testing, right? So unit testing is going to test individual software components or a collection of components. And so in particular here, testers are going to define the input domain for the units in question and ignore the rest of the system. So in particular, if you see that ignore the rest of the system, that sounds a lot like a one factor at a time, right? So if we break this down into the simplest case, unit testing is kind of akin to a one factor at a time. Right? And again, if you start digging into this, one of the most commonly mentioned techniques you'll see is this idea of a repeated running of unit tests as a regression test suite. Now I'll say by here regression, we don't mean in the statistical sense, right? So that unit test is we have these test cases for validating those testable components, and the regression testing just says, well, does the software still work as intended after a change, right? So repeated running of unit tests would just mean if I make a change to the code or I make a change to my software, I have a set of unit tests, these very basic building blocks that I'm going to see, do they still run correctly? Does the software still work as intended after a change? Right. And now one thing I will mention though is that I suspect during your course, you'll probably hear, well, one factor at a time testing is usually what we want to try to avoid in design of experiments. So say when you're testing software, however, that really is the place you should be starting off at. is that one factor at a time or the unit testing. Because in particular, the nice thing with that, when something breaks, you know exactly where to go look. And in some sense for software, if you're not even at that point, then you're not perhaps even ready yet for the whole design of experiments process. But so let's think about the test selection, right? If we think about this as a designed experiment, so given a set of inputs, which could be a whole bunch of different things when we're talking about software, but how are we going to test these effectively and efficiently, right? So that's really that selection problem. Now, one of the things with software, especially statistical software, is that typically it's deterministic, right? So if I have a data set and I want to go fit a regression model with the same data set, everything set the same, I expect to get the same results when I click fit model, right? If I come back the next day, I still expect to be seeing those same results again and again. If I have a random component, then I'll often want to keep that random seed to make sure that my results are going to be recreatable. Now, one of the other things with the type of design here, we're really looking at usually a pass-fail. Right? Effectively, did I hit what I had for that oracle? Right? Or did I have a failure in a particular test case? And so one of the big things here is that for testing software, we're really looking at fault detection rather than model fitting. So oftentimes in design of experiments, at the end of the day, there's some underlying model that we're trying to fit, which usually has parameters associated with it. But here, we're actually looking to induce failures. And ideally, if you think about from both a test engineer perspective and a developer perspective, eventually I want it to get to the point where there are no failures, right? Eventually, we want these tests to pass every single time. And so what really makes a good design though, right? So I mean, we have different criteria when we think about this from our typical design of experiments. But here, when we're talking about testing, right, we can return to that bugs lurk in corners and congregated boundaries. I mean, that's what we're going to be looking for when it comes to finding a good design. Now, depending on what you've experienced with design of experiments, so I'm going to take a step back here and just talk about, from my own perspective, usually when I think about a factorial experiment, right? So what are some good properties, or what do we think about for a designed experiment? There's this idea of effect hierarchy, right? So this really just says, well, the main effects are usually going to be the most important thing that I'm going to look at first. Then I might go to two-factor interactions, and I'm less concerned about three-way interactions, etc. Right? And so there's empirical evidence that effect hierarchy generally holds, right, when it comes to factorial experiments. Now, usually, at least when I'm thinking about the screening case, right, so that number of relatively important effects will be small. And by that, I mean, you might say, well, all of my factors I think are going to be important, but the main drivers are going to be sparse. If I really look at those most important effects, generally we may not expect there to be that many of them, that idea of effect sparsity. And then effect heredity just says, well, an interaction is going to be typically significant if at least one of the parent factors is significant. And so one of my colleagues and I, we actually said, well, what if we take these ideas and think about failure-inducing combinations? So if I want to try to break the software, what if I think about those combinations or setting those inputs in such a way as the important effects? Right? And so that actually leads us to these fundamental principles of input combinations. Right? So if we take the same approach here, what would that say for testing? So combination hierarchy says, well, combinations involving fewer inputs are more likely to be failure-inducing. Okay. And so that just says, well, I'm most likely to have a problem with a single input, which is that whole idea of unit testing and one factor at a time. On combination sparsity, it says, if I've done enough testing on my system before, then ideally that number of failure-inducing combinations is going to be small. And so combination heredity would just say, a combination is going to be more likely failure inducing if something involved in that is known to be more likely problematic. And so it actually, as it turns out, there is empirical evidence for these ideas, these fundamental principles of input combinations. So here was a study from some folks at NIST on kind of these different complex software systems. And if you see along the left there, that number of factors involved in the failure, you see for medical devices and the NASA, by the time you're at two-way combinations, that accounted for 97 and 93% of the faults or the bugs that were found within those systems. And so you look at something like a browser, so those two-way interactions, if all I focused on was two-way combinations, I've already accounted for about 76% of those different failures or bugs. And by the time you go up to those three-way combinations, now you've gotten the majority of them just by focusing on those lower order combinations. Right? So what that really says is that focusing on these ideas of combination hierarchy and ideally sparsity, is really not a bad way to go. So that sounds great, right? If that would tell us, okay, why don't we then try to focus on these different lower order combinations? So just like we usually think about main effects and two-factor interactions, well, it turns out there is a special type of design, right? What I'll call a covering array. Right? And so what's a covering array? It just says for a set of factors, a strength T covering array, or sometimes called a T covering array, has the property that for any subset of T factors, every possible combination occurs at least once. Right? So that sounds like a pretty good property. What that's saying for a covering array, if I have a strength 2 covering array, if I take any two columns, every possible combination is going to occur at least once. Now I'll say, as somebody coming from a design of experiments background, that sounds a lot like an orthogonal array, right? So in design of experiments, there's a special construct called an orthogonal array. And so the only difference in the definitions is that for an orthogonal array, each of those combinations occurs the same number of times, right? So if I have a strength 2 orthogonal array, each of those pairwise combinations occurs the same number of times. So why does it make a difference? Well, let's say this little table at the bottom here, this has to do with a binary strength 2 covering array, right? So let's just think about something like checkboxes. You go into your browser, you go into your phone, checkboxes and that, right? So a binary checked or unchecked, yes or no. That bottom row has to do with the number of inputs, right? So you can imagine if I had 1,000 inputs, 1,000 different checkboxes, if I wanted to use an orthogonal array, I would need 1,000 run or 1,000 test cases for the orthogonal array. If I use a covering array, this optimal number, that's the top number here. A covering array, I can do 1,000 inputs in 14 runs. Right, and so that's really quite magical when you think of what does that say for all of those 1,000 inputs. If I take any pair of columns, each of the combinations is going to occur at least once. And so in particular, that also means that if I can get my test to pass all of those cases, I now know that I don't have any failures due to those two-way combinations. Right, and so this falls under this idea of what we call combinatorial testing. And so I think that was what Doug had mentioned at the beginning. That's one of my areas of interest. And so combinatorial testing is so it's a family of test case selection strategies used to test complex engineered systems. And so that includes covering arrays. Now, what's the nice thing about covering arrays? Well, that actually solves that selection problem and the quality problem. Right? These covering arrays are going to help me select the cases, and it helps me assert what's actually been tested. Right? And so in particular, now I can say, well, I've tested all combinations involving up to T inputs. And so sometimes in the literature, you'll actually hear this called pseudo-exhaustive. Right? So if you think of that idea with 1,000 inputs, I'm not going to be testing 2 to the 1,000, all different possible combinations, which would be exhaustive. But by using covering arrays, we get this idea of a pseudo-exhaustive. And really, so it moves beyond that one factor at a time, or treating those single inputs as the simplest units. So just a quick demonstration of what this looks like here. So on the left, we see this covering array in 6, I'll call it, you don't have to worry that much about the notation, but all you need to worry about here is I have 5 binary inputs, so just the symbols 1 and 2. And this is a strength 2 covering array, which means that if I take any 2 columns, so if you look at those 2 red arrows, you'll see 1, 1, 1, 2, 2, 1, and 2, 2 occur somewhere within that test suite. You can do the same for the green arrows, but really the strength 2 covering array means that if I take any pair, all of those combinations are going to occur at least once. Similarly, now if I look at the one on the right, I'm going to claim here that that's actually a strength 3 covering array, which now means if I take any 3 columns, all possible combinations are going to occur at least once. Right? So that means that so 1, 1, 1, 1, 1, 2, 1, 2, 1, etc., all of the 2 to the third or 8 combinations occur somewhere within that test suite. And all that I want to point out here, this one is 12 runs, right? But it actually turns out you can do this in 10 runs if you wanted to spend the time to construct it. Okay, so this idea of covering arrays, right? You can really think of these as a specialized design experiment for testing complex systems, not just software, but complex systems in general. So why use them? Well, they're cost efficient, right? I can get these down, I'll say, to much smaller runs than what we typically think about for most designed experiments. It helps with that selection problem, right? That really tells us what to test, but as well that quality problem. Now, if I'm a test engineer, I can go back and say, well, if all the tests have passed, now I can ascertain there are no faults due to those lower order combinations. And so really I look at this as a disciplined approach to testing, but at the same time, just another tool in the tool chest. So it's not to say covering arrays are going to solve all of your issues, if you're faced with a testing challenge, but it really does help get to those corners where those bugs lurk. And just, I threw a question there at the end. So when do combination sparsity and hierarchy hold? So again, that sparsity idea, I will say that people will have problems if you try to test using covering arrays and you haven't done a lot of testing before. The problem you're going to find is that almost every single test is going to result in a failure, in which case you kind of have to get everything in order before you throw these at it. And that idea of hierarchy, so that's been an area of interest, within JUMP, that oftentimes we know where we've had problems in the past, right? Where there have been issues that certain inputs are known to be problematic. And so you can actually use that when you're trying to do your analysis. So now, just with the little bit of time I have here, I just wanted to go through a couple of examples and show one where, so this is an XGBoost. So if you haven't heard of XGBoost, right? So it's an optimized distributed gradient boosting library designed to be highly efficient, flexible, and portable. And so at least a number of years back, this was really popular in the Kaggle competitions. And but I'll say, so this is an example of a graphical user interface that we had within JUMP, that underlying would call the XGBoost library. Now imagine though, if you're a test engineer and you're told, well, look at these advanced options, go try to test XGBoost. So where do you even begin, right? So you can see there's a lot of these, like, so tree method predictor, there's a lot going on here. And so I'm not going to go through all these different inputs, but you can imagine there's more than this, but here's just some of these hyperparameters or these XGBoost selected inputs. So here I think we came up with a list of 34. Some of them are categorical, right? But some of these are continuous, which realistically has an infinite design space. So how do you go about doing that? So in software engineering, we have something called equivalence partitioning. So at least those continuous ones, you can discretize them and break them down a little bit. But so you can imagine maybe those continuous, I want to look at a kind of a high, a low, and a default, or a high, low, and mid. But I'll say, so, well, what does that mean? So if I look at all those different inputs, if I wanted to look at all those possible combinations, I guess I haven't counted how many commas, but you look here at that input space, there's no feasible way that you can consider all of those different possibilities. But if I use a strength 2 covering array, right, which just assures me that all of those pairwise combinations occur at least once, you can get a strength 2 covering array in 25 runs. So now on top of that, if I can get all those tests to pass, right, well, now I can ascertain that I don't have any failures due to those two-way combinations within those 25 runs. But on top of that, I still have 72% three-way coverage and 35% of the four-way combinations, right? So not only have we covered all the two-way combinations, we've actually covered most of those three-way combinations as well, right? And so now I can go back to my manager and say, well, I haven't done all the three-way combinations, but I can feel pretty confident that I've covered most, right? So likewise, if you went up to a strength 3 covering array, that you could do in 150 runs. And with that, then you're at 90% four-way coverage. So I just wanted to share one other example here. So this was an interesting case study that we had on testing the prediction profiler with disallowed combinations. Right. Now, if you've seen JUMP, so one of the nicest pieces that we have in JUMP is the prediction profiler. Right. So whenever you go to something like fit model, you fit a regression model. The prediction profiler lets you explore the relationships between those factors and responses. Right. So it has these plots that you can kind of slide. You can slide the axes around and see what happens when you change those inputs, what happens to the outputs. And so you can actually interact with those plots to change the values and update. Now, often we're going to use that in conjunction with the desirability function. Right. So maybe I fit a regression model and I may want to maximize the desirability. Right. So I'll say, based on the model that I've just fit, where does that model predict I'm going to get, let's say, the best yield, right, or the best output based on this model, right? So here's a really simple example of what the prediction profiler might look like. So here I actually knew what the relationship was that I fit, right? So I just have these two inputs, A and B. And so what does the profiler allow you to do? Well, I can take these crosshairs and just see what's going to happen to that function when I start moving A and B around. Right. And maybe I might ask JUMP, well, where do you predict that the best value for Y, if I wanted to maximize Y, and JUMP might tell you, well, this is where you would put those values to maximize that desirability. But so a common problem that we sometimes have that occurs in designed experiments is something called a disallowed combination. Right. So it's just a Boolean expression, could be arbitrarily complex. But for a disallowed combination, it just says, well, I want to create a design that doesn't have any of these disallowed combinations. Right. So I may tell JUMP, give me a design where at the end, I don't want any bad points in that final design. Right. And so it could be something arbitrarily simple. I could just say A times B is greater than 0.5 or less than negative 0.5. Sometimes I may have an experiment where I have an old machine and I can't use a new part on that old machine. Other examples I have here, like out of a polygon, where maybe I just wanted to place sensors all throughout the state, right? And so I may tell JUMP, disallow anything that doesn't fall within a polygon representing a map shape. Right. And so I'll see with these disallowed combinations, it's very hard to tell what an experimenter may throw at it for their disallowed combination. Right. And so here's just a simple example. I have 5 responses, Y1 to Y5, and 2 3-level categorical factors. Right, now what do we see here? I have a disallowed combination that if x1 is at level L1, the first level, then x2 can't be at L1 at the same time. Right, and if we look at the prediction profiler here, so we'll see when x1 is set to L1, well, x2, there's nothing showing there for L1. Right, now, if you were to use jump, I think it was probably back in jump 15 or 16, there would have been a value there for L1. Right, so the prediction profiler didn't know how to handle the disallowed combinations. Right, and so that paper that I was talking about, well, our task was actually to test that prediction profiler with disallowed combinations. Now, we had been working about how to maximize that desirability, but I'll say, so this was a group that had developers and test engineers with, advanced degrees in statistics, computer science, operations research, and bioinformatics. Now, one of the problems here was, well, how do you actually determine the appropriate oracle for comparing and evaluating test results? And then figure out how do we actually cover all these different possible uses. Now, in particular for the oracle problem here, you can imagine, well, did that profiler display the constrained region correctly? Does it only have allowable regions? Do the options work? Now, one of the most notable things here is that does that profiler exhibit a lag in profiling when the user interacts? So one of the beautiful parts with the profiler is just how natural and interactive that it is. Right, so if every time that I was trying to move the crosshair, if I had a big slowdown, that would be problematic for the user. Right, so in some sense, this is the kind of feature that there's a lot going on behind the scenes, but it's our job at Jump to make sure that the user is not even aware that really that much is happening. Now, what made this even more difficult for the disallowed combinations is that what do you do when you have limited data sets? So I'll say we know we have a lot of users that are using disallowed combinations, but oftentimes it may be proprietary data sets. Right, so this required us to kind of anticipate how some of these might be used. And so to do that, we actually considered both the profiler inputs as well as data set generation factors. Yes, I'm not going to spend the time going through these different factors and levels, but all that I want to point out here is that the majority of factors that we focused on were actually to generate different data sets. Right, so if you look here, almost all of the factors here, except for those bottom three, have to do with generating different types of data sets with disallowed combinations. And again, so the test suite here, if I wanted to do everything, it would have been about 1 million test cases. But a strength 2 covering array, we could actually cover all those pairwise combinations in 13 runs. Right, and in particular, all the profile options were covered. So you may say, well, what does that really mean? Like these data set generation factors. So this would be like one test case from our test suite. Right, so in those, let's say if we had that strength 2 covering array, this would have been one of the runs would be to generate a data set with disallowed combinations, to put that into the profiler, and then to check various things according to our oracle. And now I'll say with this, there is actually a sequential nature of testing. So these were run, we have a nightly unit test suite, right? So every night these tests were being run, which allows us to revisit those oracles. And then I'll say with the sequential nature of testing, so software in particular, because we can always go back and test, you can always apply these different random pieces whenever possible. And you can always add runs to improve coverage as well. So to summarize, what I hope you took away from this talk, so deriving oracles is difficult for statistical software, right? When it actually comes time to figure out what is the proper, what do I expect to get out? It's not always an easy thing. And so because it is so difficult, finding a testing mechanism that is both effective and efficient is important. And so really we can treat that using combinatorial testing. It really does boil down to a design of experiments problem. But in particular, it can handle a lot of inputs. Right, so like I'd shown back early on, you could do something like 1,000 different inputs in 13 runs. And just to point out, it can also be used for data set generation. Just some other considerations. I'll say one of the problems, because it is so cost efficient, the fault localization problem is actually quite difficult. So that says when I do find a failure, right, finding that true underlying cause can be very difficult, right? And again, that's due to that cost efficiency. Then how do you go about figuring out which is the true cause? Because whenever you analyze it, it'll look like there's a lot of different potentials. Now, it also turns out those disallowed combinations come up again when you're constructing software, right? There may be sets of inputs that don't make any sense to try to run together. So that fault localization, there's actually also more specialized kind of test suites that help you figure out where those faults are. The random seeds, making sure that you keep them. And likewise, that idea of this random inputs equivalence partitioning, boundary value analysis, that has to do with how do we take these continuous inputs and discretize them in such a way that we can use them for combinatorial testing. And just to say, so there is lots of software out there for actually constructing these covering arrays or combinatorial tests. So in JMP, you can do it in JMP Pro, but there's also products like Axe, Hexawise, testcover.com, etc. And so with that, thank you very much for your time, and happy to answer any questions in chat.
Ryan, thank you very much. This is a very, very informative talk, and I hope that that people participating in the MOOC will learn some things here, because you touched on some topics that we really don't talk about much in the MOOC. We really don't talk about covering arrays, for example, and that's something that I think that I probably should remedy. I should go back and do something with this. Thank you very much. Let me tell you a little bit about my one experience with software testing, and see if you can make some suggestions as to what I could have done better. Okay. Back in the late 70s and early 80s, I did a lot of consulting work for IBM, and mainly I was working with their development and production folks. One of the big projects that I worked on was the large motherboards that go in the big mainframe computers. These are printed circuit boards that are like 3 feet by 3 feet, in size, with 26 layers, 15 signal planes, and all sorts of crazy manufacturing problems. A lot of which involved drilling holes, so that you could, put leaded components on these boards, and dealing with, how do you do this and avoid things like drill smear, and I mean we did a lot of experimental design work, and some of the folks that I worked with said, there's a group of people here that do some extremely critical testing that maybe you should see if you could help them out. And it was a group of people in New York, I think it might have been the Kingston area somewhere, that what they did is they developed the new versions of the operating systems for these big mainframe computers. And they had a hard and fast rule that said when you make any change or development, improvement to the operating system, you can't release it unless you can demonstrate that it performs at least as well as the version that it's replacing. And they had some specific parameters, and one of them was like response time. Yep. And one of them was something called paging rate. And they had 2 or 3 of others that they considered to be things that if they deteriorated, there was going to be a problem. And so what they were trying to do was devise ways to test to see whether you can release the software. And the number of factors was not very big. They were things like what kind of application are you running on the system? Now there could be a lot of levels to that, of course. And then another factor that I remember was how many applications are running. You know, what's the workload? Okay, and then a number was how many connected users do you have? Okay, and so you know these experiments were complicated experiments to run, and obviously you wanted to reduce the number of runs as much as you could, and so what I ended up doing was creating some essentially fractional factorial designs, and you know, fairly complex fractions because there were not many factors, but they had lots of levels. You know, and so you know, tried to come up with, and I think I did a fairly reasonable job of it, but I'm sure there's probably better ways to do that today, because like I say, this was going on in the late 70s, early 80s. And a lot of the technology that I think you've talked about is much newer than that.
Well, and it's interesting you bring that up because that's the same type of challenge we still have oftentimes today. So even with all the computing power, you know, our testers have to worry about things like, well, when a new chip comes out on the Mac, right? And so there's a lot, I think from what you're talking about, there's a lot of these like environmental factors.
Yeah.
Right. And then it becomes a matter of, well, to figuring out how to partition the workload, because sometimes that also happens. So I think the way you approached it sounds like a very reasonable. And so we've actually called it sometimes like block covering arrays.
Okay.
Right. And so trying to accommodate for all of these different environmental factors, to your point, all these different levels, and to make sure that we've seen it somewhere
Yeah.
as best we can. Yeah.
Well, you know, I really struggled a lot with how to do this, and because there weren't simple ways to create mixed level fractional factorial designs.
Right.
And it was a topic that I still have a lot of interest in. Essentially, non-regular fractions. In fact, your former colleague Brad Jones and I have done a fair amount of work on non-regular fractional designs, and that's sort of what I was creating here. But I mean, if you've got a factor that has potentially 10 levels,
Yeah.
you know, all the different kinds of applications that might be running on this system, coming up with ways to come up with decent designs was difficult. I'll tell you another. I'll tell you a story about that. And we do have a question that one of our viewers has sent in, but I'll tell you this story because it's kind of humorous. I spent 4 years at the University of Washington as a faculty member from '84 to '88, and while I was there, I got to know people in the stats department, and I got to know people in the biostats program pretty well. And the guy that was head of biostats was also a Virginia Tech graduate, although he was from the stats department and I was from engineering. But he and I got to be pretty good friends, and so one day he calls me up and he says, "Would you be willing to take on one of our PhD students?" And I said, "Well, we didn't really have a PhD program in industrial engineering at that time at Washington." And I said, "Well, sure. Why do you want me to do it?" He says, "Well, she's interested in fractional factorial designs with different numbers of levels for the factors." And I said, "Wow, this is a problem I've looked at before, and I don't know a lot about it, but I'd like to work with her. I said, well, why don't you guys do it? And he said, there's nobody here that knows anything about experimental design. And this is biostats, and of course they do. And the guy I was talking to was actually one of Ray Meyer's former students. So, but anyway, so I took this young woman on, and she was really brilliant. She had worked for one of the local companies as a statistician, and had decided to come back to school. And we're working away, and she's making great progress. I mean, she's just really tearing it up. We're starting to get really interesting results. And so one day she comes into my office and says, I have good news and bad news. And I said, well, okay, what's the good news? She says, well, my old bosses called me up and said they're desperate to have me come back. And so they've offered me a massive promotion, and they're doubling my pay. And I said, well, I think I could guess what the bad news is. And she says, yeah, I'm out of here. And so I have still yet to find a student that wants to work on this, because it's kind of an ugly problem.
Yep.
It's an ugly problem. And so that was the end of my foray into mixed level fractional factorial design. Okay, we do have a question that has come in from our viewers, and I don't know if you can see this question, but let me read it to you. It says, are covering arrays deterministic? That is, given the input parameters to a covering array, do you always get back the same array?
And the usual statistician answer, I'll say it depends.
Yeah, that's my answer to everything.
That's right. So I'll say typically not, in that. So there are still a lot of, let's say, computational algorithmic constructions, right? So just like a lot of the traditional design of experiments, it's the same. But there are times where, depending on those inputs, so especially like the binary case, right? If I have a lot of those two-level inputs, the mechanisms for constructing a design are well known, and so they're more or less, it's more or less automatic in that sense. And so I'll say, once you get into the mixed level covering arrays, so just like the mixed level designs that we were just talking about, then you're much more often to see a different design that comes out. And so in the literature, we call that wildcard entries. And so what that means, sometimes there's positions in the covering array that you can do whatever you want with. And so it's not uncommon that those will change. You can throw it back to the algorithm and then try to make improvements on different criteria after you have the coverage.
And I assume that you have some criteria that you can look at. I mean, like with classical designs, we think about things like efficiency, D efficiency, G efficiency, things like that. And so you could maybe create a few different ones and somehow rank order them.
That's right.
Yeah. Did you know an individual named Charles Coburn?
Oh, he's absolutely, yeah. So he came to the SAS campus when we held the Design Analysis of Experiments conference back in 2015, I think it was. But we're big fans of him.
Well, Charlie was a faculty member here, and he and I were great friends. He is retired now. Charlie retired a couple of years ago, but I had the great opportunity to work with him on one or two of his research students. And so what I learned about covering arrays, I learned from Charlie. and he's a great teacher. And he was very patient with me, and I learned some things, particularly about the construction methods, because that's what his students were working on. And I greatly enjoyed working with him. I think he's been one of the great contributors to this field.
Yes, absolutely.
Great. Well, I do appreciate your talk. This was really quite interesting. I'll tell you one thing that I think that I believe software testers definitely need to focus on, and that's not just finding the bugs or the errors in the software, but to also think about the operational testing of the software. You know, how is it going to work when you put it into the environment where it's going to be used? And you know, there may not be any software bugs, but the function may not be correct.
Yeah.
And discovering that is really key. And of course, the example that I talked about earlier is the flight control system for the Boeing 737 MAX, which probably didn't have any bugs, but it had an operational problem, which tended to not handle stall recovery correctly, and the pilots couldn't turn it off, and they didn't figure out how to fix the problem until they'd crashed 2 airplanes and killed 750 people. And so, you know, that's something that software engineers need to think about. And I wish all of our computer science students here would take my design of experiments course, but sadly, not very many of them do. So, oh well. I'll keep preaching and hopefully some of them will get the message. Ryan, thank you so much. We're running out of time, but this was really an informative talk, and I greatly appreciate your taking time out of your day to do this.
Yeah, thank you so much for having me. I very much appreciate. I appreciate the chance for being able to talk about this.
Well, this is an important message. Thank you very much.